So the given data for this foundation problem, we are solving the isolated footing design problem today. The given data include the dead load value and live load, which are basically the reactions at the base of the column. The footing levels are known from the geotech report, fill depth, density of the soil, density of the fill, allowable bearing capacity, and the column steel. These are given, and the strength of the concrete to be used in the footing is also given. First of all, we will determine the service load, because I have told you to compute the area of the foundation. The service load is used because the factor of safety is already applied in the soil allowable bearing capacity. Therefore, the service load is sum of the dead load and the live load, which is equal to the 500 plus 700, so 1200. And then the Q allowable net will be computed. In the next step, Q allowable net is computed. So Q allowable net is equal to Q allowable minus the overburden. The overburden include the fill and the soil. So density of the fill multiplied by the thickness of the fill plus density of the soil, which is to be excavated, multiplied by the thickness of the footing, depth of the footing, that will give you the allowable net bearing pressure. So in this step, the allowable net bearing pressure is computed. Area required for the footing is total service load divided by the allowable net bearing capacity. That is computed, and it comes out to be 13.34 square meter. So if you want to compute the width of the footing and we want to provide the isolated foundation, then the width of the footing B will be the square root of the area. But if you think that no, you can go for the rectangular footing, then the area should be equal to length multiplied by the width. You can decide between these two values. Herein we go for the isolated foundation. So B is computed as 3.65 and rounded to the 3.7 meter. So footing size selected is 3.7 meter by 3.7 meter. Next step is computing the ultimate load and ultimate pressure which is developed under the footing. The ultimate load is basically equal to the total factored load 1.2 into dead plus 1.6 into live load, and the ultimate pressure will be equal to the total load divided by the area provided, because area computed may be lesser and area provided we slightly round it up. So the total pressure will be equal to the PU over A, that comes out to be 125.64 kilopascal here. We assume that when there is no movement, then the pressure is uniform, but when there is a movement, the pressure will not be uniform. And trapezoidal or other cases are possible in that case. Now the depth is the next computation, next step. Sometime we can start with some trial depth. The formula for which is written here. Sometime we can have just by judgment we can take some depth. Depth can be selected by the Also by the punching shear criteria, normally that is giving us the critical depth. Such that the applied shear lesser than the capacity of the shear capacity of the footing. So we have to provide the depth based on this criteria. But you know that even for the punching shear, the depth is unknown. We need the effective depth value. So here I have taken some trial expression, that is d is equal to the p plus moment plus 0.01 alpha sfc prime. So that comes out to be the service load divided by, this is an expression but it's empirical and it is given in some book. So I have taken it as a d value computation expression, and effective depth d is computed, so it means that the h is taken as 470 millimeter, because you know that h will be equal to the d plus cover plus half dia of the bar. So its cover in the footing is you know that 75 millimeter, because it's interacting with the soil. So where there is a soil or the water, we will normally take the larger cover so that the corrosion can be avoided for the main steel. Then comes the, so this one is the H is taken as a 470 and this gives us the effective depth value again as a 385.5. Next is that whether this trial depth is satisfied or not. So we have to see. Satisfies the punching the shear criteria. So shear check is applied. First of all, the one-way shear check. This is just like the similar with the previous shear check you have studied for the flat slab or beam, because it is taken at from the face of the support. It is taken at a distance d. So shear check will be applied. This shaded area is considered as the responsible for developing the shear. So the shaded area is how much b multiplied by the L minus C1 by 2 minus d into the total upward factored pressure. So factored pressure is already computed, Qu into L minus C1 by 2. So Qu into area will give the applied, this will be the applied one-way shear. So Qu into area 125.64 into this length is 1.24 and width, because we are computing the shear and the moment for the full width of the footing, not for the unit width. So this is multiplied with the B 3.7 meter into 1.24 is the loading length. So it gives us 576 kilonewton. Now the shear capacity is checked, and this is the expression for the shear capacity when you have already the computed the shear. The capacity expression for the one way is 1 over 6 under root fc prime bd B here, B used here is a full value of the B, not the 1 meter, but it is because the shear, applied shear is computed for the full width. So therefore, the shear capacity is checked and it comes out to be the 797.4 kilonewton. So this is satisfied. Our shear check is satisfied in one way, but you know that for the foundations, the two-way shear check is more critical, so we have to go for the two-way shear check. Two-way shear check is basically, you know, that the total load, effective load that is acting at the critical punching perimeter, which is at C1 plus D, is called as the two-way or the punching shear. So this is normally taken as the C1 plus D distance, C plus D by 2 on all sides. So perimeter become B1 and B2, where B1 is C1 plus D and B2 is C2 plus D. So in this case, our punching, we will just compute the total load which is acting in the footing at this punching area. So that is simply the total factored load acting in the total width of the footing, total area of the footing by, and then negate the load within the punching perimeter. We have to subtract the load. Normally the punching shear is slightly lesser than the applied load because you know that the applied load Pu is equal to the total factored pressure into area. Total factored pressure into the area is equal to the applied load, but the shear is not taken exactly at the column center but away from that d by 2. Therefore it will be slightly lesser than the applied load. So total load into the area outside the perimeter, total footing perimeter minus the c plus d square. So this is computed as in this form. This is the applied light punching shear. So in this way we compute the applied punching shear. Vu is equal to Qu into area. Effective area actually. This is effective area. Next step is the capacity of the punching shear. That is computed. That will be the minimum of the three criterias. First one is this one. This is the most critical one. The second one is this one, where you will use the other parameters also. The third one is this one. So for these three criterias, we will compute the punching shear capacity. All the values are already known. Alpha as this for the column location, B naught is the punching perimeter, beta C is the ratio of the longer to shorter side of the footing column. So that is equal to the, here we will compute all the values and you can see that what's the value. You see that the first criteria is normally the critical one and that gives us 1440, the minimum shear. We will select this 1440, compare with the applied shear, this is 1632. So it means that our check is not satisfied. So it means that we have to revise the depth of the footing. How to revise the depth? We can use the punching shear criteria. You can say that our applied punching shear should be equal to the VU should be equal to the 5 AC. Then you can say that you can compute the solve this equation for the unknown D. Solve this equation D value, and so by solving this equation we can get the value of the D as 436.85 millimeter, and this implies that the total thickness of the footing now comes out to be 520 millimeter. Total thickness of the footing comes out to be the 520. That was slightly higher than the previous one, so we will use the new value of the footing, that this is the effective depth from this expressions, and H is then about 85 millimeter is added in the effective depth, so H gives a 520. So this is the new depth of the footing, effective depth of the footing. Next come the design for the flexure. So we will not revise all the previous calculations, but only the new depth is used for the new calculations. When you revise the depth, no need to reapply the shear check, because the shear check was already applied, and now the new depth will definitely satisfy the previous shear checks, which was already satisfied, because now the depth is higher, and even the punching shear check which was failed will be satisfied. Now come the movement in the foundation. So you know that just like a shear, the movement will also be the, in addition to the loading length, the it will also be multiplied with the movement arm. So resultant of the load, because it is an isolated footing, so load is acting on the one side of the footing. So movement will be equal to the, and we are computing the movement for the full width of the footing. So therefore we can compute it by this expression Qu into the width of the footing, that is the loading value. This is the loading length B by 2 minus C1 by 2, and then we multiply it by the half of this loading length, because the moment arm will be half of this. So this will give you the bending moment in the isolated footing. You can see all the values, how you have to use all these values are given. From that we can compute the steel ratio rho value. Again remember that we are using the full width, so for the rho value also the full width is used. Full width of the footing, we are not computing for the 1 meter. When we are using the full width, it means that the reinforcement will also be computed for the complete footing, not for the unit width. So this gives us the ratio equal to the 0.00238, and you can see that this ratio is larger than the rho minimum, but you should recompute the AS minimum. Rather than comparing the rho with the rho minimum, we should compare the AS with the AS minimum. So AS minimum is 0.001 at BH. As for the ACI slab minimum, the criteria for the AS minimum is also similar. So we can compare, we can see that it is larger than that, and rho BD is computed as 3841. Total steel is needed. This one we have already selected the number 19 bars. So number of bars can be computed as AS over area of the one bar. So area of the one bar is 284 and area of steel is this one. So 14 bars are needed. Then the spacing can be computed by this expression. So total width of the footing divided by the number of bars can give you the spacing of the footing. So that is that should be less than 450. So we obtain that 264. So it means that 4 number 19 bar total bars are needed, or you can say that you need the number 19 at 266 millimeter center to center. In this way you can compute the flexural design of the footing. So what we have done here, the three steps are done here. First of all, the width of the footing is decided. Second, the thickness of the footing is decided. And third one, the reinforcement in the footing is decided. This reinforcement will be provided on the bottom side of the footing. So now we will start with the joint design. Next one. This was the foundation design, and I hope that you have understand. If you have any questions, you can ask. Now the joint design is to be carried out. The dowels reinforcement is to be designed now. So so in the foundation design, joint design, I have explained that why we need the joint to compute whether these dowels are needed and how much dowel bar, which are shown in the red colors, are shown here. And this we obtain by first computing the column area, and then we project the column area to the footing bottom by the slope of 1 vertical to 2 horizontal, and this area is obtained, which is shown in the blue color, in the brown color rectangle, because area 1 is the column area and area 2 is the projected column area at the bottom of the footing. This is with reference to the 1:2 vertical slope. Why we compute it? Because this formula is used, this one, the second one, to compute the bearing strength in the footing, because bearing of the column is this one, the first expression, and we will use this expression. Now if our column load is lesser than the bearing strength, column load is lesser than the bearing strength, then we have to go for the minimum dowels. But when the column load become larger than the bearing strength, then we have to go for the dowel. The dowel expression steel computation is this given here. So in this way we design the dowel steel. Now come back to the problem. So here we are starting with the column to footing connection detail design of dowels. First of all, the bearing strength of the column at the base of the column. This is the expression for the bearing strength at the base of the column. But you know that the bearing strength, footing width is larger than the column width. Therefore, the bearing strength at the base of the footing length will be computed. So that is 0.85 FC prime A1 into A2 by A1, where A1 is the area of the column and A2 is the projected area. So how to compute the projected area? You know that this one is the area of the column and projected area A2 will be computed by this is the width of that. Dimension of the projected area A2 will be 0.45 is the column width plus 2 into 0.52. Thickness of the footing is 0.52. So you know that the slope is going with 2 into 2 time the vertical. So 1 into 2 vertical. So that's why the horizontal slope is equal to the 2 times the thickness of the footing on one side and 2 times the thickness of footing on the other side. So on the all side it will be, and then we add the column dimension in that. So total dimension of the projected area is 2.53 and the area will comes out to be 2.53 multiplied by the 2.53. So this gives us the A2, but as per the code requirement, A2 by A1 should not be larger than 2 and it is larger than 2 here. So we will use the value of 2 here. So the formula for the bearing strength, this one shown in the brown color, is now used. We use the 2 value only for the A2 by A1 and the remaining is the all values are known. A1, FC prime 0.85 and 5. All values are here put and then we compute the capacity of the. So we see that the capacity of the footing is much larger than the column load. Column load was about 1720 kilonewton. It means that the minimum dowels are needed. So the minimum number the area of dowel is required. So as per the ACI criteria, the minimum dowels are 0.005 AG, and we can compute these dowels requirements, and then the number of the bars can be computed by the dowel steel area divided by the area of the one bar. So we are using the same dowels bars normally which are for the column steel. So 4 dowels are needed. So 4 corner steel of the columns will be lapped with the dowel bars spliced and which will be extended to the foundations. Now the question is that if the phi Pn is not less than Pu and Pu become larger, then you need to apply this expression for computing the dowel steel. Now how much is the splice length of the dowel and how much is the mm, extension of this? So we need to compute this development length and splice lengths for the reinforcement detailing. Normally you are computing even for all kind of detailing, but as you will study this topic and normally you need to compute the development length. Why? Because the bottom steel cannot be curtailed. The steel in tension must be before the LD plus the effective depth. We need to see these development length because if you cut the steel before the development length, what happens that full bond strength is not developed. Full bond strength is not developed. So there are some formulas which I have taken from the ACI code and used here for the development length and tension, for the development length and compression, for computation of splice length. So all these are used. Why these are used, I will let you know one by one. For the bottom steel of the footing, because this will be in the tension. So that steel development length is computed. It means that all the bottom bars cannot be curtailed before the LD plus D beyond the critical section. Footing bottom steel. This is for the footing bottom steel that cannot be curtailed before LD plus D. So it comes out to be 865 and D value is approximately 435. So 435 plus 865. So we will see that how much is the available length, but our foundation bottom steel should be beyond the critical section. The bottom steel of the footing should at least be that much extended. If it is not available, we can make the hook and make it in the upward direction. If the larger length is available, we can curtail the 50% of the steel. But if the larger length is not available in the footing, then we have to make the hook and make it turn upward 90 degree. Second case is that what is the splice length? So we will use the compression steel dowels in the columns also. So how much is the dowels extension in the footing? So dowel bars are extended into the footing equal to the LD compression, because this is the compression steel. The column was in compression totally. So we will compute the LD compression and we will extend the dowel steel. Then the splice length. This much is the extension of the dowel steel is needed in the foundation. So we have already the depth available in the footing. So we will extend that, but you know that uh, the vertical length available for the extension is not that much. So we have to take 90-degree bend is required, and the total extension of this dowel bars in the footing, this vertical plus horizontal, should be equal to the LD. The third one is the LD splice length, that how much is the splice is needed for the column steel shown in the purple color and the red bar shown in the red color, the dowel bars. So we have to compute the splice length. So last one we compute the splice length. If our column steel is in tension, then we will use the tension splice length 1.3 LD. If it is in compression, then we will use the compression splice length. So I have used that, we written all the expressions. So relevant length you will pick and you will apply in the foundation detailing. So in this way, finally the detailing of the foundation is carried out. Bottom steel is provided on the both side, but no need to design the other side, because you know that the D will be slightly lesser. But practically speaking, we will provide the same steel on both sides because the load is same. Only the effective depth is slightly lesser in the other direction, but we will not reduce the steel in that direction. We will not change it because it's just minor changes. So just we will design the one side. But if the it is a rectangular footing, then you have to design for the two sides. So based on today lecture, you guys are required to repeat the same problem for the other case. One case is that rather than concentric load, consider also some eccentricity for this problem, and then try to work on this problem. And the third case is that making this foundation eccentric as well as the uh, rectangular footing, then see that what changes occur. So all possibility you must see based on the available time. I can finish this problem. So please try to solve the other two cases also when there are the eccentricity present in one or two directions, and when it is a rectangular footing, then also solve the same problem. All data is same, but only that the two data are changed. So if you have any question from this problem, you can ask. Thank you very much.
नो सर, थैंक यू। काफ़ी अच्छा था सर, काफ़ी फ्लो में समझ आई है।
Yes.